Okay, this is section 11.3. We're going to be doing integration on trigonometric functions. So that is, we're going to be learning the antiderivatives of some trig functions. Okay, so we have already talked about calculus and trigonometry. You learned 6 formulas for the derivatives of trig functions. The derivative of sine, the derivative of cosine, the derivative of tangent, the derivative of cotangent, the derivative of secant, so we're doing derivatives here, and the derivative of cosecant. Now I want you to rack your brains and see if you can remember these 6 derivative formulas. At one point you were very good, you knew them all. We had quizzes in which I drilled you and made sure that you knew these 6 derivative formulas. Okay, so once you're sure that you know those and you fill them all in, then I want you to go ahead and write out them backwards for the antiderivatives. Okay, now that we have these 6 backwards derivative formulas, or 6 antiderivative formulas, we're going to do a couple of example problems using them. And so notice on questions 1, 2, and 3, I'm doing integrals, which are antiderivatives. None of them are definite integrals, meaning there's no number at the top or bottom here. And so my answers are just the antiderivative functions with a plus c. Okay, so on number 1, this would require possibly a u substitution. But I'm going to show you how to do this without a u substitution. We need to start taking a little bit of a shortcut when the u substitution would be simple. Okay? So whose derivative, remember when we do an integral, we're asking whose derivative or what's the antiderivative of sine. So whose derivative is sine? Well, it's sort of cosine, right? The derivative of cosine is actually negative sine, and I would have to have the 2x in there because that part never changes, right? Whatever's inside stays the same. So maybe this antiderivative is cosine of 2x. I know it's not, though, because the derivative of cosine is negative sine. So I must have had a negative to start with, so that when I did the derivative of negative cosine of x, I got negative sine of 2x. Because the derivative of cosine is negative sine, and then those would cancel, and I'd have back to the original that I have there. But also, when I had done this derivative, I should have multiplied by 2 because of the chain rule. Because this inside part, the 2x, has a derivative of 2. So when I multiplied by 2, when I did the chain rule, I don't see a 2 there. That means that in the original function, I must have started off with a 1/2 already there, and then the 2's cancel. Okay, this would have played out in a u substitution as follows. So you would have let u be 2x, and when you did the du dx, you would have gotten 2. When you rearranged to find dx, you would get du over 2. And then you would have integrated sine of u du. And then that antiderivative is negative cosine of u. And then you would have over 2. There would be a 1/2. So negative 1/2 cosine of u. And then you would have back substituted and gotten the 2x in there. And so what I'm doing is I'm bypassing literally all of these steps with the u substitution. And that is what we should do as long as the derivative is a constant number. If the derivative is 2, then just go ahead and say, look, u would have been 2x. The derivative is just 2, so divide by that for a reverse chain rule. Now, and so this is my answer with a plus c. That's the answer for number 1. Let's look at number 2. Number 2 is different because you have to do a u substitution here. Because we should let u be the inside. And when I take the derivative of the u, I don't get a simple number. I actually get something with x in it. That means I need to do the u substitution and hopefully cancel that out. So this would change to x times the cosine of u, and dx would revert to, I forgot to solve, du over 6x. And notice the x's did cancel like I thought they should. And I have 1/6 integral cosine of u du. And the antiderivative of cosine is sine. And so our answer here is 1/6 sine of 3x squared minus 2 plus c. So that one, yes, do the u substitution, don't do the shortcut. Okay, and now let's do number 3. This also requires a u substitution. I'm just going to do this in blue because we're a little crowded here. What should I let u equal? Well, there are a lot of things that you can see in here. It's secant of square root of x times tangent of square root of x divided by square root of x. I'm going to think of the fact that the square root of x is inside both the secant and the tangent. And I'm going to also remember that secant, tangent, that's familiar. That's the derivative of secant. And so he would actually be an easy antiderivative to do because that's one of my antiderivative formulas. It's just the square root of x that's throwing me off. So I'm going to go ahead and let u be the square root of x, which is x to the 1/2, which I want to write that way so that when I find the derivative, 1/2 x to the negative 1/2, it's easier to solve, or easier to do the derivative. So this was 2x to the 1/2. I'm going to cross multiply here. So 2x to the 1/2 du, that's what dx is. And so when I rewrite my original integral, I have secant of u, tangent of u, because those were the guys who I was meaning to replace, because that's an antiderivative I can do. The dx changes to 2x to the 1/2 du. And notice I'm still divided by square root of x, which I could have called u, but I'm going to go ahead and keep it as square root of x because that's x to the 1/2, and now those cancel. And so I just have 2 integral secant u tangent u du. And that's a formula. Secant u tangent u, he's the derivative of secant. So the answer is 2 secant of u, and then I should back substitute to square root of x. And there we go. Okay, moving on. Those were 6. So these first 6 formulas that you did, I'm going to go back to them. These were the backwards formulas from the 6 derivative formulas that you had to know. So we learned that the antiderivative of cosine is sine, the antiderivative of sine is negative cosine, antiderivative of secant squared is tangent, and so on and so forth. But what we're missing in this list, see, we have sine and cosine. But I would just like to know, what's the antiderivative of tangent? What is that? And what about the antiderivative of secant? Who is he? Just the secant. I know the antiderivative of secant times tangent because that's the derivative of secant. But what if I just have secant of x? And so we're going to learn those as well. I am going to go ahead and take about 5 minutes and derive 2 of them for you, and then we'll just learn the other 2. They're very similar. Okay, so for tangent, this is a very simple derivation. What you want to do is write this as sine of x over cosine of x dx. Right? Tangent is the same as sine over cosine. We're going to do a u substitution and let u be the denominator, the cosine of x. The derivative of cosine is negative sine. And so notice that that's going to cancel. So du over negative sine of x is dx. And so when I rewrite this integral of tangent of x, of sine of x over cosine of x, I'll have sine of x over u, and then dx will be replaced with du divided by the negative sine of x. So the sine of x is canceled, and I have negative du over u. And what's the antiderivative of du over u? That's natural log of u. That's what we learned just most recently. And so if I back substitute, let's see, I get negative natural log of cosine of x plus c. And so that's our new formula, that the antiderivative of tangent of x is the negative natural log of cosine of x plus c. And on the next page, I have these all written out nicely for us to copy down and put in a big box. Okay, now this next one is really very sneaky. The way that this works is not very completely simple. But what we're going to do is we're going to, for cosecant of x, we're going to multiply this by a very crafty form of the number 1. So we're multiplying it by 1. That doesn't change it. But the form of 1 that I'm going to use is cosecant x plus cotangent x. I might come back and change this. It's been a while since I've derived this. Divided by cosecant of x plus cotangent of x. Okay. So now I'm going to, now this cosecant of x, that's over 1. And so when I distribute cosecant, I get cosecant squared x plus cosecant x cotangent x. And that's divided by cosecant x plus cotangent x. So all I did was distribute this cosecant of x to the numerator of the 1 that I multiplied by. And then the denominator is just, when I multiply 1 by cosecant x plus cotangent of x, I just have cosecant plus cotangent. Okay, so now we're all primed to set up to do a u substitution. I'm going to let u be this whole denominator. And the derivative of this, you're going to see it's miraculous. What's the derivative of cosecant? Well, the derivative of cosecant is negative cosecant cotangent. Negative cosecant cotangent. And then what about the derivative of cotangent? Well, the derivative of cotangent is negative cosecant squared. Negative cosecant squared. Is that a coincidence? No. See how my crafty form of 1 just worked out perfectly? Okay, so then when I multiply, or when I solve for dx, I'm going to factor out that negative, and I'm going to rearrange. So that's cosecant squared x plus cosecant x cotangent x. That's what equals dx. And so my integral rewrites to this numerator, which I highlighted certain parts in green, cosecant squared x plus cosecant x cotangent x. The bottom I let be u, and then the dx changes to du over, and then that negative factored out, cosecant squared plus cotangent x cosecant, I wrote that, it's the same thing. And so those cancel. Shock, right? This whole, I can put this in parentheses and cancels except for the negative. So this is essentially integral negative 1 over u du. And so that's negative natural log of u. And my u was that strange cosecant x plus cotangent x. And so that's the formula for the derivative of cosecant of x. Yay. Now, the derivatives of cotangent and the derivative of secant are or antiderivatives, are very similar. And so these are the 4 trig, or the 4 additional trig antiderivatives to learn. Just a note about these, I know these are absolute values here. Technically, these are supposed to be absolute values. But I'm not going to care if you use parentheses or absolute values. That's a technicality we're just not going to get into in this class. Okay. Now I just have a couple of more examples. This example says, find the average value. It's been a while since you knew what the average value is. There's a definition for average value. What is the definition of the average value of f on an interval AB? Let's see if you can remember that. What is the definition of the average value of f on AB? That's what it is. So for us, 1 over b minus a, pi fourths minus negative pi fourths, integral from a to b, negative pi fourths to pi fourths, of secant of x. Okay, and so now I need to do the antiderivative of the secant of x. So this is pi fourths plus pi fourths is 2 pi fourths or pi halves, so 1 over pi halves. What's the antiderivative of secant? Well, if you look in your formula, it's the natural log of the absolute value of secant x plus tangent x. Now, this is not a plus c because we have a definite integral. We're going from negative pi fourths to pi fourths. So I'm going to plug those two numbers in and subtract. So I have 1 over pi halves natural log of the secant of pi fourths plus the tangent of pi fourths minus the natural log of the secant of negative pi fourths plus the tangent of negative pi fourths. So I've just simply plugged in pi fourths and negative pi fourths. Okay, so let's evaluate these. The secant of pi fourths, that's 1 over the cosine of pi fourths, this is square root of 2. And the tangent of pi fourths is 1. And so we're doing the natural log of 1 plus the square root of 2. I don't know what that is. Now, negative pi fourths is in quadrant 4, and cosine there is still positive. So this is square root of 2 here. Now, negative pi fourths in quadrant 4, the tangent of things in quadrant 4 is negative. So this is minus 1. And so this is minus the natural log of the square root of 2 minus 1. And I want to multiply that by 1 over pi halves. Okay. And that's going to be my final answer, whatever that number is. You could type it into a calculator to find a decimal approximation, but that's just fine. Oh, by the way, before I forget, the book will write this answer differently. They love to use log properties. And so they will combine a log minus a log into one logarithm in which you divide. And they might even rationalize that, which would be crazy. I'm going to write 1 over pi halves as 2 over pi. It's the same thing. So here's a somewhat better answer. Same answer, though. Okay, I think this is the last example. Yes. Find the area of the indicated region. I want to find the area between 0 and pi halves under this curve. That means I just do the definite integral from 0 to pi halves of 1 minus x squared plus cosine of x dx. So you're just going to do the antiderivative of this, plug in pi halves 0, and subtract. And you guessed it, this is what you are going to do on your own at home.